Okay, so deep breath. We did we added that one pipeline stage up here, this one here, and then we had to deal with this backwards wire. Right, this idea that we're making a branch decision here and doing some computation that affected what we wanted to do in the earlier pipeline stage, and that caused us to add some hardware and do some annulment and deal with that. Okay, let's go ahead and continue our exploration about adding additional pipeline stages. So let's add a few more. Let's make sure the instruction memory, the register file, the ALU, and the load and store data fetch are all in different pipeline stages. So each of our piggy blocks, our time-consuming blocks, is now in a separate pipeline stage. Our hope is to get, well, if the gods were really with us, we'd get a 4x improvement, but maybe we'll get a 2.5 or a 3 times improvement in the cycle time, and that's still worth doing. Okay, so just as we had to deal with this information flowing backward in the pipeline here, in this particular picture, notice that the register file is really being treated, the read ports are up here and the write port is down here. It's the same register file, but conceptually the writes are happening way down here in the last pipeline stage, while the reads are happening in a much earlier pipeline stage. So there's an implicit transfer of information from this stage, when we change a register, to this stage when the register is read. So in this case, the backwards wire, okay, has to do with the contents of a particular register in the register file, the one that's being written down here. And if I happen to have, at some earlier point, been reading that register hoping to get a result from some earlier instruction, it may or may not be in the register file. It depends whether that instruction has finished its progress through the pipeline stage and has actually gotten to the point where it's writing the information in the register file. Yes? Yep.
After a branch, but meanwhile with your hardware you've implemented an annulment, won't that essentially destroy the program?
Yes, so the compiler has to know what the hardware is doing. And in general, most modern compilers make a very conservative assumption that work on every implementation, say of an x86 processor. It's possible to tell the compiler that you know this will be executing on a very particular processor. The modern compilers know a lot about the details of each generation of Intel processor, and they'll actually work on instruction scheduling, knowing that you're doing. The Intel hardware is designed to work correctly, even if you get the instruction scheduling wrong, but it will work much more efficiently if the instruction schedule that the compiler compiled actually is running on the processor that it knew about. So in general, you don't want to come up with a hardware implementation that simply breaks. Okay, you were trying to get higher performance, but if you break all the existing programs, no one's ever going to buy your higher performance machine. So in general, you shouldn't make, the compiler writers and the hardware implementers shouldn't make inconsistent choices about, for instance, how branch delay slots are dealt with. Okay, so we're hoping for a reasonable improvement in the cycle time, maybe 2.5, 3, I don't know. We'd have to do some of the arithmetic carefully. But right the moment we're interested in what other semantic changes has this cost us. We have to worry a little bit about now, are there things like branch delay slots that will cause the programs to suddenly execute incorrectly unless we go fix them. So we're going to get a start on fixing that. We're thinking about that now, and then in the next lecture we'll deal with all the things we don't get to today. Okay, so notice what the pipeline, so it makes pretty, so the two operands are being fed into the ALU, the write data is being pipelined so it can be fed to the memory at the right moment. The instructions are certainly being pipelined down so that each stage knows what its operation should be. Notice that the PC+4 value is also a piece of information that has to be sent through the pipeline, because actually it's not until we get right to the end where we might have to write PC+4 in the cases of branches and jumps and things like that into the register file. So what the registers here represent all the information that's needed for the successful execution of the remaining stages for a particular instruction. So we have to make sure to pass all this down. So we've actually these are big 32-bit registers. And so, the register cost in this is non-trivial, but our hope is that our processor will be noticeably faster. So in the modern world, we have a lot of transistors in our budget, billions and billions. Let's spend them on making higher performance machines. That's sort of what we're thinking. Okay. And this is just talking a little bit about what's contained in some of those pipeline registers. So how does this work? Well, as usual, we'll start off with an example showing it working really well. And so here's a program. And there's something interesting about this program. Notice that all the registers that are being changed by each instruction, so the add C is changing R2, the sub C is changing R3, the XOR is changing R1. Notice that I've changed R2 here, but none of these instructions refers to R2. Right, so in some sense, even though this instruction will eventually change the contents of R2 in the register file, when the add C instruction gets to the write-back stage, none of the earlier instructions care about the contents of R2, so that will be fine. So in fact, this particular set of operations works well. It's at this point, magic point here, right at the end of cycle I+3, at the end of the write-back stage, that the add C finally will update the contents of R2, but none of the mul, XOR, or sub C used R2, so we're all set. Right? I'm sorry? Oh, I'm sorry, but it needs to be able to read it in the register file stage, right? So it's okay for the mul to be in the instruction fetch stage. Good catch. Thank you for correcting my thing. So the use of when does the mul instruction use R2? When it needs to get the contents of R2 from the register file, right? And that happens when the mul is in cycle I+4, when the mul is in the RF stage. So happy with that? Did I take my foot out of my mouth? Good. Okay. Alrighty. So far, so good. But of course, there's an example that works less well. So here's an example that works less well, and it's pretty easy to see what the less well part is. The add instruction is writing its destination register as R3. Here's the add instruction in the write-back stage. That means the write to the register file happens at the clock edge that's the boundary between I+3 and clock cycle I+4. And that means these blue shaded guys here, starting at this point, is when the contents of R3 are actually available out of the register file. So it's at this clock edge that the register file actually gets updated with the result of the add instruction. Where does the first place I try to read R3 from the register file? Well, the compare instruction, the RA register for the compare instruction, in fact, is reading R3. And that means, if we think a little bit about it, that I need to be able to read R3 from the register file in that cycle. Okay? It is available here. I'm trying to read it there. If I look in the register file, the number I'm looking for isn't there yet. So can the compare instruction successfully complete its RF stage operations? The job of the compare instruction in the RF stage, or put it the other way, the job of the RF stage when it sees the compare instruction is to say, I'm going to go get the operands. And the operands are the constant 100, appropriately assigned extended, and the contents of register 3. So that's supposed to happen by the end of this cycle, but I can't do it. Does everybody see what the problem is? I'm looking in the register file, the answer hasn't put out there. Because of the way I've done the pipelining, that write isn't happening until later. Okay. Oops. So I hope I made clear what the problem is, right? I'm trying to get something before it's where it belongs.